Hello everyone, today I'm going to be doing a classic Faradays problem for you. Now this problem is from Spring 2025, Midterm 1B number 3. I'll start off by reading the problem. A ring made of thin wire is placed in a magnetic field, given here. The radius of the ring is oscillating at r equals 2 minus sine of 10t meters. Find the magnitude and direction of the induced current. The resistivity of the wire is 0.5 ohm per meter. So as for any Faraday's problem, we're asked to find the magnitude and the direction of the induced current. First, I'll look at our givens. We're given the B field, and we can see it has x, y, and z components, and it has function cosine 60t. Next, we're given the radius of the ring, which is oscillating. We're given it as r equals 2 minus sine 10t meters. Finally, we're given the resistivity of the wire is 0.5 ohm per meter. We should also note that we're given that the ring is made of thin wire. Now this means we only have one loop, and that will tell us that our n here is equal to 1. Now I want to look at the given diagram. We're given x and z, and we also need to find y. Now I'll do this by using the right hand rule. Now when you have your right hand out flat, open palm, your fingers will always be in the direction of x. Your thumb, which is out, will always be in the direction of z, and your palm will always be in the direction of y. So putting my fingers in the direction of x, my thumb in the direction of z, we can see that our palm will be pointing into the page. And what this tells us is that our y-axis will be into the page, and I will mark that here on the right side as y going into the page. Now, our first step into the problem, first we want to find our magnetic flux, which is equal to B dot dA. So let's identify our B and our A. So our B is given here, and our A, which is our area. Well, first we want to figure out whether or not we need to do this integral. Now we can see that our integral is with respect to area, so we want to see if either our radius or if any of our components are changing with respect to area. Now we can see that this is not the case, as both of our functions are changing with respect to time but not area. Now this allows us to simplify our flux equation into simply B dot A, and now this is a simple dot product, and this equals the magnitude of B times the magnitude of A times cosine theta, which is the angle between the two vectors. Now our area vector will be perpendicular to our given ring, so we can choose either negative y for it to be in the negative y direction or the positive y direction. And then our B field has components in the x, y, and z direction. Now when you take the dot product, we only care about the components that they have in common with each other. Now as the area vector has no x or z component, we can ignore those in our calculations. So effectively, our B field is just B equals negative 4 y hat cosine 60t. And for our area, we have our given is radius, and the area of a circle is just pi r squared, which I'll write here. Area equals pi r squared. And what is our r? R is given, r equals 2 minus sine 10t. And as for our angle, cosine theta, I will choose our area vector to be in the same direction as our B field, which is the negative y direction. So our angle will be 0, and cosine of 0 is 1. So to find our flux, we just have to multiply the magnitudes of B and A. So here we have equals B times A. And putting that together, finally we have our flux is equal to -4 cosine 60t times pi r squared. Now r I will use as in place of our variable, or in place of our radius, for the sake of space and time. And as for our next step, we want to find our V EMF, which we can now do because we figured out our flux. In order to do that, we need to take the derivative of our flux with respect to time. We can see that we'll have to use the product rule in order to do this. Now, as a reminder for the product rule, well, I'll write it out. If you have two functions multiplied together, let's say f of x times g of x, and you take the derivative of them, that is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. Now here we have our two functions, which are b and a. So our, as mentioned before, our n is 1. So our V EMF is just equal to, using the product rule, will be b derivative of b times a, or let's write this as db dt times a plus b times dA dt. We have a negative for all of that, around all of that. So let's figure out what each of these components are. First, our a and b are given. So first we want to find dB dt. Now what is dB dt? That's the derivative of -4 cosine 60t. Let's take this out. There should not be this. Okay. So the derivative of -4, let's write it out. Oops. dB dt is equal to, taking out this, the derivative of cosine is negative sine, so the signs will cancel. So we have our left width is 4 times 60, which is 240 sine 60t. As you know, the 60 would come out due to chain rule. Next, we want to find our dA dt. Now, what is our dA dt? Let's write it out. dA dt. What is this equal to? We have the pi r squared. The derivative of pi r squared will be 2 pi r. And for to consider chain rule, we also need dr dt. Now, what is dr dt? That's the derivative of our given r. Let's find that as well. dr dt is equal to, the 2 cancels, so we just need the derivative of sine 10t. That will be, or negative sine 10t will be -10 cosine 10t. Okay. Now that we have all the components, we just have to put it together. So our final value for VEMF, let's see, let's write it out. VEMF is equal to -240 sine 60t. That's dB dt, and their area is just pi r squared. Pi r squared, and adding the second component, you have a value for b, which is 4 cosine 60t. And the negatives will cancel for this component. And then we have our dA dt, which will be 2 pi r dr dt. Okay. And plugging in for dr dt, we have VEMF is equal to -240 sine 60t times pi r squared minus 80 cosine 60t pi r times cosine 10t. Okay, and that is our final value for VEMF. Now at this point, either we can find the magnitude of our induced magnetic field, or what I like to do first is find the direction of the induced, or current, I mean not induced magnetic field, the direction of the induced current and the magnitude of the induced current. Now I like to find the direction first, because on a midterm, when you're on a time crunch, the direction can be found at this point, and this will be a bigger indicator of your understanding of the problem compared to the magnitude, because finding the magnitude is just basic algebra. So to find the direction, you can do this because this function that we found for VEMF will be the same as the function that you will use for I induced. You'll just be dividing it by resistance. So the behavior will be the same. Now, Lenz's law says that, well, first let's go with Faraday's law. Faraday's law tells us that if there is a changing magnetic field, this will cause an induced current to appear. And Lenz's law tells us that a system wants to object to change. So if there is a change in magnetic field, there will be an induced magnetic field that will oppose that change. Same with current. If there is a change in current, there will be an induced current that will oppose the change. Now, how do we find this? We want to find the term of this function that's dominating under small t conditions. Now, what does this mean? When our function is just starting up at very small t values, we want to know the behavior of our functions. So we want to know if either our given B field will be dominating or if our equation for radius will be dominating. And then we'll look at the behavior of those equations to identify the behavior of the system. Now, how do we do this? We want to look at this equation, and we can effectively plug in t equals 0 as a replacement to check the behavior. Now we have a sign here, and sine 0 is 0. So what will that do? That will cancel out this portion of the function. And then we have cosine, two cosine portions on the right side. Now cosine of 0 is 1, so we're just left with this term. So now we know that this term is dominating. But how do we know which term this is? Now we want to look at the derivatives. In this term we had dr dt, so we know this term is correlated to dr dt. And in this term we had dB dt. So in this term, if this term dominated, we would know it'd be related to our magnetic field. So our dr dt comes from our dA dt, right? So we know that, let's write this out. At t equals 0 plus, we have figured out that dr dt dominates. Now, what do we do with this information? We want to look back at our equation for radius and figure out whether it's increasing or decreasing at the start. So we have r equals 2 minus sine 10t. Now, the function is what we want to look at, sine 10t. Let me draw it out up here. This is what sine looks like. Now, if you look at the start, we can see it's increasing at the start. So we know that this portion is increasing, but it's subtracted 2 minus sine 10t. So if we're subtracting an increase, we're actually decreasing overall. So now we know that the radius of our circle is decreasing at the start. So flux is basically the amount of magnetic flux is basically the amount of flux going through an area. So if either our magnitude of our magnetic field is decreasing or our area is decreasing, our flux is decreasing. So here because our area is decreasing, we'll have less magnetic field going through the loop. Now our magnetic field is going in the negative y direction, correct? So we know that we're decreasing in the direction that's coming out of the page. So here I'll write that B fields in the negative y direction coming out of the page is decreasing. Now Lenz's law tells us excuse me, that it will oppose this change and produce a induced magnetic field in the opposite direction. So coming out of the page will be increasing to compensate. Now using the right hand rule for curl, placing your thumb in the direction of the B field, the direction your fingers curl in will tell you the direction of your induced current. So putting my thumb in the direction of the induced current, I can tell that my fingers are curling in the counterclockwise direction. So I'll write that down. I induced CCW counterclockwise, or you can write that circling in this direction. Now this is the first part of our problem complete, which is the induced current. Now the last part of our problem is finding the magnitude. Now here we know that our equation for induced current is V EMF over R. So let's start with that. I induced equals V EMF over R. Now this R is resistance. This R should not be confused with the radius. Now we're not given resistance in this problem, we're given resistivity. So how do we find the resistance? This is simply found using the length of the loop multiplied by the resistance. How do we find the length of the loop? That's simply the circumference of a circle, which is 2 pi r. We have r as radius. So I can write that down here. We have resistance, R resistance is equal to rho, which is resistivity, times length. And our length here is 2 pi r, so we can write rho times 2 pi r is equal to our R resistance. Now we have VMF as well. So plugging everything in, we have, let's see, we have negative 240 sine 60t pi r squared minus 80 cosine 60t times pi r cosine 10t. And plugging in for resistance, we have rho is 0.5 as given. So plug that in, 0.5 times 2 pi r. Now the 0.5 and the 2 will cancel out to 1. Then we'll be left with pi r at the bottom. Now we can cancel this with the numerator. Now these will cancel, and pi r will cancel with this pi r, as well as this pi and this r. Now we can simplify this to our final equation. What is our final equation? I induced equals negative 240 r sine 60t. I'll subtract this by 80 times cosine of 60t multiplied by cosine of 10t. This is all in amperes. So this is our second component of our final answer. That's the magnitude, and we found the direction earlier. Now, it's up to you whether you want to find the magnitude over the direction first. As mentioned before, I like to find the direction first. Now let's go over Faraday's problems overall. Generally, you want to look at your givens, identify your givens, identify your missing axis, and then you want to find the magnetic flux here. Figure out whether or not you need to do the derivative by looking at your givens and see if any of it relies on dA or anything is changing with area. In our problem, we only had items changing with time, so we did not have to take the integral. And then you find the VEMF from your given flux. After that, you want to find the term that dominates within your equation. And using the term that dominates, you can use Lenz's law to figure out the direction of your changing magnetic field, and then your induced magnetic field, and then your induced currents. And then finally, we found the magnitude of our induced current. And I hope this was helpful. Thank you for watching, and good luck.